So in this video, I'd like to talk to you about atoms and subatomic particles. So when we're looking at the periodic table of the elements, there's several different things that we're going to be seeing in terms of the relative information. First thing you're going to see with any element in the periodic table of the elements is the atomic number. Recall that the atomic number always tells you the number of protons in an atom of that element. So for example, with hydrogen, we would see an atomic number of 1. And that atomic number of 1 tells us that an atom of hydrogen has 1 proton. Now, assuming that this atom has not engaged in a chemical reaction, this 1 proton will also happen to equal the number of electrons that this atom has. So if that atom of hydrogen has not engaged in a chemical bond or has not undergone chemical reaction, not only will it have 1 proton, but it will also have 1 electron. Now understand, we don't get this information from the atomic number. We can never assume this simply from the atomic number. So the only information we get from the atomic number is the number of protons. Okay. Cut. So I'd like to talk to you about various characteristics of atoms, subatomic particles, and some key information that you're going to find in the periodic table of the elements. So let's go ahead and just start by talking about an atom. Now recall from lecture that an atom is the smallest unit of an element that still retains the properties of that element. And as such, these atoms are going to contain 3 subatomic particles. The first of these subatomic particles will be what are called the neutrons. Second will be protons. And the third will be electrons. Now, 2 of these subatomic particles are going to have charges associated with them, and those are going to be the protons and the electrons. The protons have a positive charge, while the electrons have a negative charge. The neutrons are going to have no charge, so they are electrically neutral. So we've got these 3 subatomic particles, and let's talk about how they're arranged in an atom. So if we look at any kind of atom, we're going to notice that that atom has what's commonly called an atomic nucleus. This is going to exist at the center of the atom. The nucleus is going to be composed of protons and neutrons. Circling that nucleus we will have electrons. So electrons are going to orbit the nucleus. Now I've drawn it in a linear kind of fashion, or at least a planar fashion here, where they're orbiting around this path, but understand that really what's happening is these electrons exist in what's known as an electron cloud, which just represents a volume surrounding the nucleus where these electrons can be found at any given point in time. So, protons and neutrons are in the atomic nucleus, electrons are orbiting that atomic nucleus. Now there are a couple of other key aspects regarding elements and atoms that I'd like to address in regards to the electrons, the protons, the neutrons, and other information. So let's talk about looking at an element inside of the periodic table of the elements. So let's, for example, look at the element lithium, Li. So if you go to a periodic table and you locate lithium, you'll find that it has an atomic number of 3. So let's go ahead and discuss what the atomic number means. The atomic number tells you one key aspect of whatever element you're looking at. And that aspect is the number of protons. So that's the number of protons that you can find in that particular element. Okay? So, atomic number, number of protons. You can't figure out the number of electrons, and you cannot figure out the number of neutrons if all you're given is the atomic number. You need additional information. So, atomic number only tells you the number of protons. So here, with lithium, if it has an atomic number of 3, that means that an atom of lithium would have 3 protons in its nucleus. Aside from that, we have no idea how many electrons or neutrons it would have if we're not given that information. Okay? So, that's atomic number. Outside of atomic number, we also have what is known as the atomic mass. Okay? The atomic mass is going to be the total mass of the atom, that is, protons, neutrons, and electrons. But we also have something else. Okay? So atomic mass is going to be the mass of the protons plus the neutrons plus the electrons. These electrons, though, are incredibly small subatomic particles, and as such, they're not going to have a whole lot of mass. So what you're going to find is that the atomic mass usually also looks very similar to the mass number. Okay? And the mass number is simply protons plus neutrons. And recall from lecture that these two subatomic particles have similar masses to each other. So, for instance, if I had, say, carbon-12. Okay? So, carbon-12. Carbon has an atomic number of 6, which tells us it has what? It has 6 protons. Okay? 12 here is going to be our mass number in this particular instance. So the mass number is protons plus neutrons. We know that it's got 6 protons. So to calculate the number of neutrons it has, we simply take the 12 and subtract 6 from it, leaving us with 6. So carbon-12 would have 6 neutrons. So, again, review. The atomic number only tells us the number of protons. To determine the number of neutrons, you need the mass number and the atomic number. You can then subtract the atomic number from the mass number, and what you're left with is the number of neutrons. If you want to determine the number of electrons, you need to know if this atom has or has not engaged in some form of chemical bond. If it has not engaged in a chemical bond, then you may assume that the number of protons equals the number of electrons. So if I tell you that carbon has not engaged in a chemical bond, you may assume that it has a total of 6 electrons, giving it an electrically neutral charge. That's only if I tell you it has not engaged in a chemical bond or gone through a chemical reaction. Okay? So, the information that you need to determine the number of subatomic particles in any atom is as follows. To determine the number of protons, you need to know the atomic number. That's all you need. To determine the number of neutrons, you need the atomic number to give you the number of protons, and you need the mass number to tell you what the relative mass is. Remember, the mass of neutrons equals the mass of the protons. And finally, to get the number of electrons, you need the atomic number to first of all know the number of protons, and you need to know that the atom has not engaged in a bond or a reaction. This is the information you need to know. All right, so let's take a step back here and let's start looking again at the atoms and what these electrons are going to look like when they're arranged in these atoms. So, I'm going to just assume that you'll understand that when I draw the atomic nucleus and label it with a certain, say, let's go ahead and do hydrogen. So when I label it like this, and then I have an electron surrounding it, okay, orbiting it, I expect you to understand that this nucleus represents the protons and neutrons inside of that nucleus. So I'm not going to draw the protons and neutrons. You're going to have to keep tabs on this. And you can do that by looking at a periodic table and looking at the atomic number and the mass number. Okay? So let's talk about what's going on here. So I've got hydrogen, and I've got this electron orbiting that hydrogen. Let's go ahead and draw another atom. Okay. So here is sodium, and I'm going to draw the electrons around sodium, look like this. Okay. So, both hydrogen and sodium have electrons orbiting their nucleus, and these electrons exist in these differing levels of energy, or they're at least lumped together by scientists based upon the relative amount of potential energy. So these two electrons are in the same layer here because they have the same level of potential energy, approximately. These 8, 1, 2, 3, 4, 5, 6, 7, 8, are in the same layer because they have approximately the same level of potential energy. And then this one is by itself because it has a different level of potential energy than the ones here in the second layer or the ones in this first layer. These differing levels of energy are called electron shells. So electron shells represent groupings of electrons based on potential energy. Okay? And remember that the difference in terms of the energy is such that the closer the shell is to the nucleus, the lower the level of potential energy. So, for example here, hydrogen only has one electron in its outermost shell, while sodium also only has one electron in its outermost shell. But the question I'd like to ask and pose to you at this point in time is, which of these electrons, these single electrons, this one here in hydrogen's outermost shell, or this one here in sodium's outermost shell, which one has the highest level of potential energy? And the answer is, of course, this one here. Because remember, the farther away from the nucleus, the higher the level of potential energy. So this electron represents the electron that has the highest level of potential energy, and it's here in the third shell. So notice how these shells are categorized. We can have a maximum of 2 electrons that fall into the category of the first shell. We can have a maximum of 8 in the second shell, and we can have a maximum of 8 also in that third shell. So we've got 1 electron here in the first shell of hydrogen. Here in sodium we have 2 electrons in the first shell, 8 electrons in the second shell, and then 1 electron in the final shell. Right? So, shells, they represent potential energy. This is different from orbitals. Orbitals represent space where the electrons orbit around the nucleus. And they are tied to a degree to the shells. For instance, these 2 electrons in the first shell also happen to be in the space classified as the 1s orbital. When you go to the second shell, all of the orbitals are denoted with the number 2. So we'll have 2 electrons in the 2s orbital, and then the remaining electrons will be in the 2p orbitals. When we go to the third shell, all of the orbitals are preceded with the number 3. So we have 3p, and anything else along those lines in regards to those orbitals. Okay? So, those are the electron shells. Now, another thing to remember is if an electron moves from a lower shell to a higher shell, so if it goes from the inside or closer to the nucleus to farther away from the nucleus, that electron has to absorb energy to do so. Your electrons are going from a lower state of energy to a higher state of energy. They have to absorb energy to get there. Okay? Conversely, if an electron moves from an outer shell to an inner shell, it's going to release energy as it does so. So if this electron were to move from the third shell down to the second, or from the third to the first, it would lose energy as it did so. Okay? Now, of course, I brought to light the fact that we have single electrons in the outermost shells. Remember that those outermost shells are called the valence shells. So these are valence electrons. Valence electrons are going to be electrons that occupy the outermost shell of an atom. So here, for hydrogen, the valence shell is the first shell. For sodium, the valence shell is the third shell. So, valence shell for hydrogen is the first. It has 1 electron in its valence shell. Sodium, on the other hand, its valence shell is the third shell, and it has 1 valence electron as well. So, this is essentially what I wanted to introduce in regards to atoms. Remember that these valence electrons are going to be the electrons that are ultimately involved in chemical bonds. And that's why we spent so much time talking about them. Again, the shells represent layers of energy, and we classify the electrons based upon the amount of potential energy they have, and that's how we categorize them into these shells. And that orbitals represent the space that the electrons can be found 90% of the time when they're orbiting the nucleus. Right? So this is the introduction to atoms, the various characteristics of those atoms, the arrangement of electrons into shells, as well as the classification of valence shells and valence electrons.